Okay, for MCCB, the equation that we use for overcurrent is 1.75 times FLA, and then for the cable is 1.25 times with FLA. And then for the fuse, we use for the overcurrent 1.25 times FLA, and for the wire we use 1.25 times FLA. Okay, this is the example of the full load amperes for single phase AC motors. Okay, so as you can see here, this row is the horsepower. So as we know that motors related to the horsepower 1 to 1.5 and so on, and then this is all the voltage, and this is the equation, this is the data for the full load amperes. Okay, so you see next slide for the details. Okay, we look at this example of this how to identify what is the sizing for the circuit breaker. So design a circuit to serve a 10 horsepower 240 volts single phase AC motor. So the overcurrent device is a MCB. Okay, so the solution is we have to refer to the previous table for FLA. As we look at here, it is around 200, 230, 240, and then this one, the horsepower is 10, okay, and then 230, and we see here the FLA is 50. That's why we use here is 50 amps, okay. And then for the overcurrent, we have to use the previous equation, this one, okay. So you just 1.75 times 50, so you get 87.5 amperes. And then so if we refer to the catalog, okay, the catalog from the supplier, there is no circuit breaker for 87.5. So approximately we choose 100 amps single pole. And then for the wire, for the cable, we use 1.25 times 50, equivalent to 62.5 amperes. Okay. So this is why this one is for the MCB, and this one is for the cable, the sizing of the cable. So and then in some cases, the circuits will serve several motors. Okay, not only one but several motors. So for MCCB or MCB, normally for the overcurrent, we use this equation 1.75 times FLA largest motor plus sum of FLA for smaller motors. For the cable, 1.25 times FLA largest motor plus sum of FLA for smaller motors. Then for the fuse, we use same equations for the overcurrent and also conductor or wired, which is 1.25 times FLA largest motor plus sum of FLA for smallest motors. So we look at the example here. So an air conditioning unit has two motors, okay, a 5 horsepower compressor and a 1 horsepower condensing fan. So both motors are rated at 240 volt, which is the single phase. So design a circuit for this unit using MCB as the overcurrent devices for protection. So for the solution, we have to refer to the table FLA. So FLA 5 horsepower is 28 amps, and FLA for 1 horsepower is 8 amps. Okay. Okay. So for in order you want to determine the current rating or the sizing for the MCB. So we have to consider for the overcurrent cases. Okay, so we have to use the equation as I mentioned before, this one, OC, for the overcurrent protection. Okay, so this is, we can use this equation either for MCB, MCCB is okay, okay? So MCB normally used for the single phase, MCCB we use for the three phase. So you can use this equation either for the MCB or MCCB. So to determine what is the current rating for the MCB, so we use the previous equation, then we use 1.75 times with the FLA largest motor plus sum of FLA for smallest motors. Okay, so for the largest motor, 28 here, okay, this one, and then the smallest motor is 8. So when you sum up, okay, you times and you sum, will get 57 ampere. So approximately we can choose around 60 ampere one pole MCB. And then for the wire or the conductor, we use the same equation, the previous equation, 1.25 times this one, 1 times FLA, largest motor, plus sum of FLA for smaller motors, then you can get 43 amps. So this one is the approximately current, this is the current rating that can be used in order to choose the sizing for the conductor. Okay, and then for the transformers, okay, for the transformers also we have to consider the overcurrent device, the overcurrent protection for this transformer. Okay, so transformer must have overcurrent device protection on both sides, which is the primary and secondary side. So as we know, transformers have the primary and secondary. So both of these sides must have the overcurrent device protection. So for the primary side, we can use this equation. It is the same equation for the primary and also the secondary. Okay. So and then the FLA is determined from the transformer's rated kVA and voltage, not the load current. So we have to identify what is the transformer's rated kVA, the current from the transformers, from the transformers, which we consider the kVA, which is the apparent voltage, apparent power, and also the voltage, not the load current side. Okay. Okay. So we can see here, we look at the example. So example, a 50 kVA, this one is S, okay, S, step down transformer with a 3.3 kV three-phase primary. So we have the primary side is 3.3 kV and 415 volt secondary. This one is the secondary voltage is selected to serve a lighting panel. Okay, so select the correct overcurrent device for this transformer. So we have to identify what is the suitable current device for this transformer. Okay. Okay. So in order to calculate, you have to understand regarding the transformer. Okay. So basically, for the transformer, for the design, the electrical design for the transformer, so we have here is the supply, and then we have the MCB here, then we have the primary, the secondary, and we have back the MCB. Okay, and then go to the load. Okay, so this one is the primary. This one is the secondary. Okay, so secondary. So for primary, as in the questions, say that 3.3 kV, and secondary is 415 volt. Okay, so here you have to identify first what is the I, the current for the primary, and the current for the secondary. So you have to use the equation. You have to use the equation S equals to 3I phase V phase. Okay, so you know that V phase equivalent to V line to line divided by Z3. So we have here S equals to 3I phase V line to line over Z3. Okay, then you'll get S equal to Z3 I V line to line. Okay, so I equivalent to S you divide by Z3 V line to line. So here is the equation. Okay, so S you divide by V line to line times with the Z3. Then this is this one is for the primary side. You got 8.75 ampere, and then this one is for the secondary side. You get 69.56 ampere. So you can determine the MCCB circuit breaker for this transformer. So if for the transformer, you just times 1.25. Okay, based on the previous equation, you just times 1.25 times with the FLE, which is the primary side you get from the equation. So you got is 10.94 ampere for the primary side. Okay, so approximately around 50 amp. Okay, three phase, three poles, and then you use the MCCB. Okay, so this one you can use for the secondary side. You times 1.25 with the FLA, you get 86.95 ampere. So approximately you can choose 90 amps three phase MCCB. That one is for the transformers. Okay, this is the panel box. The panel, how to, this one, panel box and also the switch box. So normally the connected load that connects to all these boards is, some of them is the lighting, the air conditioning, the water heater, ceiling fan, refrigerator, lift, and booster pump. So we have, in order we want to calculate the maximum demand, we have to consider the demand factor. So this demand factor is based on the usage, our usage. It is not a fixed value, but this is based on our assumption on our lifestyle.